Now this is the second bonus video. Now I am proving the linearity of divergence. Okay, so we have a divergence of a scalar a times vector a plus scalar b times vector v. Okay, so this is equal to the a times divergence of a plus b times divergence of b. We have to prove this. Okay, so we will take this, so we will expand this del by del x cap plus del by del y cap, and of course we know that this a and b are the scalar quantity which is a constant, and a and b is a vector, okay, which is a function of x, y and z. So it is a scalar field, vector field. Okay, so this is the we are taking the divergence of a. Here we will write ax x cap plus this is ay y cap plus az z cap. Okay, so this is yeah, so this is the first term, plus we have this bx x cap plus by y cap plus bz z cap. Okay, and remember this ax ay az bx by bz each this component will be the function of x, y and z individually. So we are taking the so yeah, what we are going to do, we will do this. Okay, so we will take the dot product. Okay, so this is the first term. Okay, first of all, before doing that, let me rewrite this. This is going ax, okay, a times ax okay, b times bx this is x cap. It is going to be much easier in this way. This is a times ay plus b times by y cap plus a times az plus b times bz z cap. Now taking the dot product. Okay, so that means we are doing like this, the x dot x. So this is the first x and this is the second x. Okay, in the similar way, when we take this operation with this, so the derivative will act on this, but this x dot y will give a 0. In the same way, if we take this and operate on this, so in the similar way, the x dot z will give 0. So in the similar way, if we take the second term, operate on this, the x dot y will be 0, and then this term with this will give d by dy a times ay plus b times by and then y dot y. Okay, and then this term with this term, y dot z is 0. Okay, now this term with this term, z dot x is 0 and z dot y is 0, and so will be 0 and 0, plus the final term, this dot this is not 0, del by del z a times az plus b times bz. Okay, and then we have z dot z. So this is 1, this is 1 and this is 1. So we have L by del x a times ax plus b times bx plus del by del y a times ay b times by plus del by del z a time az plus b time bz. Okay, so now we have just this differential, I mean partial derivative acting on this function. So partial derivative follow the linearity properties. So what we can do is write like this: del by del x, okay, ax plus, so this is the first term we are taking, and then we'll take this term and this term, a times del by del x ay, sorry, this is del y because we are taking this term, plus a times del by del z az. So this is the first thing we are doing, and in similar way we can write like write for the b also: b times del by del x bx plus b times del by del y by, and then b times del by del z bz. Okay, so we can also factor out a and write del by del x x cap plus del by del y y cap. Okay, so we can write like this now: plus del by del z z cap times a of x x cap plus a of y y cap, a of z z cap. In the similar way we can write b into exactly the same term, okay, times this b of x x cap plus b of y y cap plus b of z z cap. Okay, and we know, okay, so how this is, so if we take this gradient of this a, so this is nothing but the gradient of a plus b times gradient of b. Okay, so we have proved it. The gradient of a plus b of b is this term. Okay, so how we are getting this from this? Okay, so once you just multiply this two thing, you will get the same thing, you will get this thing.